Welcome students. Today we discuss Poisson distribution. So first we derive the distribution function for Poisson distribution. We discussed that Poisson distribution as a limiting case of binomial distribution. That means Poisson distribution is derived from the binomial distribution with help of some assumption. We use the distribution function of binomial distribution to derive the Poisson distribution. So, to derive the Poisson distribution from the binomial distribution, this concept is known as Poisson distribution as a limiting case of binomial distribution. So, Poisson distribution is a limiting case of binomial distribution under the following condition. First condition is that n, the number of trial, is indefinitely large. It means n approaches toward infinity. So, to derive the Poisson distribution from the binomial distribution, our first assumption is that n is very large. That means n approaches toward infinity. Second assumption is that p, the constant probability of a success for each trial, is indefinitely small. So, p approaches toward 0. Indefinitely small means that this p approaches toward 0. Third assumption is that np. We know that np is a mean of binomial distribution, and third condition is that np equals to lambda is a finite. So, by using these three conditions, we derive a Poisson distribution from a binomial distribution. Then, for a binomial distribution, we know that probability function is given by CNR p raised to power r q raised to power n minus r. So, if we solve this combination, we know that this is equals to n factorial over r factorial over n minus r factorial. So, if we solve n factorial, this is equals to n, n minus 1, n minus 2, n minus r minus 1, and next term is n minus r factorial. So, n minus r factorial in the numerator and denominator are cancel out, and this is a r factorial. P raised to power as it is, and we put the value of q. We know that p plus q is equals to 1. So, the value of q equals to 1 minus p raised to power n minus r. Then, after solving this combination and putting the value of q in terms of p, then next term is n, n minus 1, n minus 2, up to so on n minus r plus 1 over r factorial. We put the value of p by using this. We write np equals to lambda. So, if we find the value of p, p equals to lambda over n. We find the value of p from the third assumption, np equals to lambda, then value of p equals to lambda over n raised to power r. 1 minus lambda over n raised to power n minus r. We put the value of p as lambda by n. Then from this, lambda raised to power r written here, r factorial written here, n minus 1, n minus 2, n minus r plus 1 over this n raised to power r written over that factor. And this factor is broken into two parts, 1 minus lambda over raised to power n and 1 minus lambda over n raised to power minus r. So, this is equals to 1 minus lambda raised to power n, and here if we can write 1 minus lambda over n raised to power minus r, and if we shift this minus r into the numerator, this becomes 1 minus lambda over n raised to power r. So, this lambda raised to power r as it is, r factorial as it is, n. Now, this n raised to power r is write as n into n into n into n r times. So, this n raised to power r can be written as n into n into n into n r times. So, first n is adjust with the first factor, second with the second factor, third with the third factor, and r with the rth factor. So n over n, n minus 1 over n, n minus 2 over n, n minus r plus 1 over n, this factor as it is. Now if we simplify this factor, lambda raised to power r over r as it is, n into n cancel out, this become a 1. So this is equals to n over n is 1, 1 minus 1 over n. Next vector n minus n is 1, 1 minus 2 over n. And this factor n over n is 1. If we take minus is common here, this factor become a r minus 1 over n. And now we rewrite that factor. This factor can be rewritten as 1 minus lambda over n raised to power minus n over lambda. We multiplied and divide with the minus lambda. So if we multiplied and divide with the minus lambda, then we can take the condition as n approaches toward infinity. As we write, this is our first assumption. As n approaches toward infinity, each of these factors, if we here put n approaches toward infinity, 1 over infinity is 0. So this become a 1. Similarly, 1 minus 2 over n, 2 over infinity is 0. This is a 1. So all these factors are equals to 1 or approaches toward 1 as n approaches toward infinity. Also, this factor 1 minus lambda over n raised to power r. If we write n approaches toward infinity, this factor become a 0 and 1 raised to power r is equals to 1. Also, we have the one property that as limit x approaches toward plus infinity or minus infinity, 1 plus x raised to power x is equals to e. So, because our n approaches toward infinity, so 1 minus lambda over n raised to power minus n over lambda, this factor approaches toward e. So the answer of this factor is e raised to power this minus lambda as it is. So we simplify all these terms, all these product terms, e approaches toward 1. This factor is also approaches toward 1. And the value of this is e raised to power minus lambda. So if we write all these, hence in the limiting case when n approaches toward infinity, we write pxr equals to lambda raised to power r e raised to power lambda over r factorial, where our r varies from 0, 1, 2, 3 up to so on, where lambda is finite number and value of lambda equals to np. So the equation 1 is called a Poisson distribution. So as we discussed, from the binomial distribution we derive a Poisson distribution under some assumption. That's why Poisson distribution is known as a limiting case of binomial distribution. Now we write some remarks regarding the Poisson distribution. First is lambda is called the parameter of the distribution. As we discussed, to find the binomial distribution we require the two parameters n and p, but for the Poisson distribution we required only one parameter, that is a lambda. Next is mean of Poisson distribution is lambda, variance of Poisson distribution is also equals to lambda. So in the Poisson distribution, mean and variance are equal and both equals to lambda, that is the parameter of the distribution. Now we discuss some important properties of Poisson distribution. First property is that Poisson distribution is a discrete probability distribution. As we check Poisson distribution, find the probability at a particular point. As we write here, r equals to 0, r equals to 1, 2, 3 up to so on. So this distribution is a discrete probability distribution. Second property is that in the case of Poisson distribution, n is indefinitely large. So n approaches toward infinity. Next we discuss that p is indefinitely small. So p approaches towards 0. And next we write np equals to lambda. Parameter is finite. The next property, mean and variance of Poisson distribution are equal to lambda. Next property, sum of the probabilities PR for R equals to 1, 2, 3 up to so on. This is equals to 1. So the sum of the probability is equals to 1. So these are the 6 are the properties of Poisson distribution. Now we discuss the few numerical based upon Poisson distribution. Fit a Poisson distribution to the following data and calculate the theoretical frequencies. Values of x are given and corresponding frequencies are given. Value of x is 0, 1, 2, 3, 4. F is given 122, 60, 15, 2 and 1. It is given that e raised to power minus 0.5 equals to 0.61. So, first we required the parameter of the Poisson distribution. We know that the parameter of the Poisson distribution is lambda. And we know that lambda is equals to the mean, and this is our discrete distribution. So mean equals to summation fx over summation f. We find the value of lambda 0 into 122 plus 1 into 62 into 15, 3 into 2 plus 4 into 1 over the sum of all the frequencies. So this is equals to 100 over 200, 1 over 2, and this is equals to 0.5. And we know that Poisson distribution is given by n into e raised to power minus lambda, lambda raised to power r over r factorial, where this n is sum of all the frequencies. This n is the sum of all the frequencies. So this n equals to 200. So the probability function is given by 200 because we find the value of lambda is 0.5. 0.5 raised to power r e raised to power minus 0.5 over r factorial. Now we can put the value of e raised to power minus 0.5 as 0.61. So if we simplify, this is equals to 122.5 raised to power r over r factorial. Now the distribution fitting, Poisson distribution fitting is given from that table. Firstly, we write the values of r 0, 1, 2, 3, 4 because the values of x are 0, 1, 2, 3, 4, 5 and 6. Then we write the probabilities. First we find the probability at a 0. To find the probability at a 0, here we put the value of r is 0. So this is equals to 122.5 raised to power 0 over 0 factorial. 0 factorial is 1. 0.5 raised to power 0 is 1. This is equals to 122. So then we put r is 1. So this theoretical frequency is 122. If we put r is 1, 122.5 raised to power 1 over 1 factorial. If we simplify that, this is equals to 61. Similarly, here we can put r equals to 2 and find the next frequency. R equals to 3. We find the probability corresponding to 3. R equals to 4. And then we write here after a rounding off. We calculate the sum of this is also equals to 200. So this is known as a fitting of binomial distribution. So fitting of binomial distribution means we calculate the theoretical frequency with the help of Poisson distribution function. Now we discuss one more example. The probability that a man aged 50 years will die within a year is 0.01125. What is the probability that of 12 such men, at least 11 will reach their 51st birthday? So the probability that the man aged 50 years will die within a year is given as 0.1125. Total number of men is given 12. We want to check that at least 11 will reach their 51st birthday. So we take P as a probability that a man aged 50 years will die within a year. So the man will die within a year is this. N is 12. So we find the value of lambda. We know that lambda equals to N into P. So 12 into 0.01125.135. Let x denote the number of man aged 50 years who will die within a year. So we suppose that the number x denotes the number of person whose age is 50 years and that die within a year. We know that by Poisson distribution the probability is given by using this. Now we want to find the probability that at least 11 will reach their 51st birthday. So if 11 will reach their 51st birthday, that means at most one die within a year, because the total number is 12. So 11 will reach the 51st birthday, that means one man die within a year. So that means at most, so probability, we can write probability of x is less than equals to 1. Less than equals to 1 means we write the probability at x equals to 0 and 1. At 0 we write e raised to power minus lambda, lambda raised to power 0 over 0 factorial. At 1, lambda raised to power 1, e raised to power minus lambda over 1 factorial. So if we simplify and after substituting the value, we get our answer is 0.9916. Thank you.